Why most of the foods are perishable in nature? These foods have very low shelf life, and the aim of preserving food is to increase the shelf life, and we simply freeze, we simply put the food in the freezer, in the refrigerator. Basically, we decrease the temperature, and with this, shelf life is increased. But how is this possible? Basically, the foods, they are having the high entropy S, right? So when we decrease the temperature, the entropy decreases, right? So basically, it is the high entropy which deteriorates our food, which decreases the shelf life of food. So we have to lower the entropy of the food by keeping the food in the freezer or in refrigerator. Simply we have to decrease the temperature to decrease the entropy of the food. So this is related to the third law of thermodynamics, which states that entropy of a perfect crystal at absolute zero is zero. What? Entropy is zero at 0 Kelvin. There is no doubt that food is not a perfect crystal because it is made up of, it is a heterogeneous substance containing carbohydrates, proteins, fats, minerals, and water. But we can reduce the entropy. So in this way, we can increase its shelf life. So mathematically, we can say that limit temperature tends to zero, entropy will be zero, but for the perfect crystal. There is nothing like perfect crystal, but the characteristics of perfect crystal are they are having a highly regular and repeating cell units. There are no defects such as vacancies, dislocations, or impurities in the perfect crystal. And the third thing is perfect crystal exhibits high symmetry. If any substance is having these three characteristics, we can categorize them into perfect crystal. In food science, the crystalline structure of these components can significantly affect the texture, stability, and quality of the final product. The formation and control ice crystals are crucial in frozen food processing. The size and distribution of ice crystals can impact the texture, mouthfeel, and quality of frozen foods. You will never like to taste the ice cream having large ice crystals because it will give you the bad mouthfeel. You will feel the sandy-like texture. So you will only prefer the ice cream having the smooth texture. And this is possible only when you will be able to control its crystallization. So you have to put the conditions in such a way that small ice crystals are produced in the ice cream. By definition, we can write entropy S is equivalent to Boltzmann's constant into natural log omega, which is microstate, number of microstates. So entropy will be equivalent to Boltzmann's constant into number of microstates present in that crystal. Boltzmann's constant is basically it is a fundamental physical constant that relates the average kinetic energy of particles in gas with the temperature of that gas, and its value is approximately 1.38 into 10 raised power minus 23 joule per Kelvin, right? And for perfect crystal, for perfect crystal, omega is equivalent to 1. So for perfect crystal, we have only one microstate present. So if we substitute this in this equation, we will get S entropy is equivalent to Kb constant, Boltzmann's constant, into ln 1. So it will be S equivalent to 0. So for perfect crystal, the entropy is 0, right? At 0 temperature, 0 Kelvin. Now we can relate that temperature dependence of entropy, dependence of entropy, and we know that the heat capacity Q is equivalent to heat capacity is equivalent to C delta T, right? And we know and also we know the entropy S is equivalent to Q upon T, right? Let's write them in differential form. We can write this equation as ds is equivalent to dq divided by T, right? And we can also write this equation as dq is equivalent to C dt, right? So we can substitute this dq in this equation, and we will get this equation as ds will be equivalent to dq sorry we will get ds equivalent to C dt divided by T. Now let's integrate this equation, and we will get S equivalent to, from 0 to T temperature, C dt divided by T. S will be equivalent to C ln T minus ln 0, and it can be reduced to S equivalent to C ln T, or we can write this as S entropy will be equivalent to 2.303 C log temperature. Why is it impossible to obtain 0 Kelvin? Why is it not possible? First reason is that Heisenberg's uncertainty principle. This violates this principle if we can achieve the 0 Kelvin. As per the Heisenberg's uncertainty principle, it is impossible to simultaneously know both exact position and momentum of a particle. So if we are going to achieve 0 Kelvin, there will be 0 momentum, and when a particle is having 0 momentum, its position can be easily located. So this goes against the Heisenberg's uncertainty principle. This is the one reason that why we cannot achieve 0 Kelvin. Another reason is that as the system's temperature decreases, the efficiency of cooling method diminishes. Extracting the remaining heat becomes increasingly difficult, requiring exponentially more energy and time to achieve further cooling. Because we know that if we have a material with the temperature, high temperature difference T1 and T2, so there is the heat transfer is very high. And when this difference becomes less with time, it becomes very difficult to extract heat, to transfer heat from one surface to another surface. So this is one more reason that why is it difficult to obtain 0 Kelvin, because when we go down and down to decrease the temperature, it becomes very difficult to extract further heat from the system. The third reason for this is all real materials contain some level of impurities and defects. So these imperfections can interfere with the ability to remove all thermal energy from the system. And the last reason is in practice, experimental setups are subjected to limitations, such as background radiation, heat leak, and other environmental factors that introduce unwanted thermal energy. So these are some reasons that why it is impossible to achieve 0 Kelvin.